He got his master degree in science from NITT. He pursued a master in technology and a doctorate of philosophy from the Indian Institute of Technology, Kharagpur, India. He had 12 years of teaching technical experience in network engineering and instrumentation engineering at IIT Kharagpur and 16 years of teaching experience. Currently, he is working as a professor of Department of Computer Science and Engineering at GITAM University, Bangalore. He has published papers in more than 100 international journals and conferences. Content-based image and video retrieval, multimedia information retrieval from distributed environment, medical image analysis, object tracking in motion video, and cognitive science is the research area of this professor. He received the Young Scientist Award from the Department of Science and Technology, Government of India in 2007, Indo-US Research Fellow Award by Indo-US Science and Technology Forum in 2008, and Obama Singh Knowledge Initiative Award in 2013. Now the session hand over to our resource person, Dr. A.Vadivel. Sir, please hand over the session.
And Madam, thanks for the nice introduction. And,
thank you, sir.
Thanks for giving me the opportunity to interact with all my faculty colleagues. I would like to share my presentation. Could you allow me? Ma'am? Can you make me as a co-host or something like that? Yeah. Whether my screen is visible to you, madam?
Sir, it's visible, sir.
Okay. Okay. Today we will discuss on the facial expression problem, and I'll also discuss some of the machine learning algorithms used for classifying the facial expression. So that will be the idea. I will be discussing two papers published from our side on the facial expression. And if you have any further clarification, etc., you can download the paper, and I'll give you the DOI number. You can download and then have a look at it. Again, through the course of the interaction, if you have any clarification or doubt, you can stop me at the same point. We will discuss and then proceed further. Please do not postpone your queries or questions to the end of the session. If you do so, then you will forget the question, then I'll forget the answer. Okay, so we will try to make this session as interactive as possible. So whenever you have something to interact, please do interact. Okay. So let us start. Facial expression is, very, very important real-time applications. Say, for example, in recent times, there is a concept or there is a domain of application is called AI ties. Okay, artificial intelligence ties. Now, in this, if you have, say, for example, a tie like this, and in earlier cases, you will be having a remote and with a lot of buttons, and this remote will interact with the tie. This fellow will run and then tilt, etc., etc. But now the AI tie has been modified with all the expression-based applications, such that if I am the owner of the tie, right? So I have my face. Okay, then I will interact with the ties. The toy will listen to me, so it recognizes my voice, and it also recognizes my mood. It also recognizes my expression. It also recognizes my state of mind by reading my face. So here, this fellow reads the face and then the facial expression. Accordingly, the toy will be, acting. A kind of, simple, the miniature of robotics for a particular application. So this is the recent application. Lot of, the research is happening. And the second application where you can use the facial expression is in interrogation. You know that, the police people use interrogation mechanisms. Now you cannot beat anyone in the police station, lawfully. But if you want to extract the, the fact of, the crime or whatever it is, then you need to understand. So there is a lie detector technology used by forensic people. Now that has been, enhanced with the facial expression again. Okay, say if I make a statement and a statement is, saying something, and if it is, real, or if it is fact, then accordingly there will be, the expression relation, okay, or state of the mind, expression, etc. There will be a relationship. So that could be measured. And another area is computer vision, especially in robotics. Okay. Likewise, there are so many real-time applications where the expression, emotion of a human is being, used. Maybe if someone is really interested in, extending their research, actor Shivaji Ganesan. Okay. So when Shivaji Ganesan is acting, it will be so perfect, right? So say, for example, he cries, right? Now, can you write an algorithm by reading his face that no, he is crying, for acting, not real? Can you discriminate, right? Likewise, there are a lot of fun-based applications in research where the real-time facial applications can be measured, estimated, okay? And you can do a lot of things with that. So with that kind of, the introduction, the first part of my presentation is on a paper we have submitted. It's published in 2020 to measure the facial expression of a human, and we proposed a novel graph called interval graph. Okay, so this is where the novel concept of the algorithm, and this interval graph we have used for identifying and classifying the facial expression of a human being, right? So now this is what the DOI of the paper. It's published in MTAP 2020 papers, later 2020. It's an interesting paper. If you are really interested, you can download it and then have a look at it, right? Okay. So now let me introduce the problem. The problem is to measure the facial expression of a human. Okay, we are not going to estimate the facial expression of something else. We are estimating the facial expression of human, right? And it can be used for many of the real-time applications. I have listed one or two popular applications, and there are so many, because it will be very tedious for me to list out all, and it is time consuming as well. Okay. Now there are a lot of methods proposed by both academia, especially the university level academia, and industry for measuring the facial expression. But in this paper, we have introduced a novel interval graph of facial region, and from the interval graph we will be extracting the features and then estimating the emotions and the expression through that, right? What we do, so we used to use the concept of common intersecting points. Okay, so all these, the blah blahs, I will explain in detail when I go to the next slide. Okay, but the last point is we have used the data set, a very popular data set called JAFE, a Japanese facial expression data set. And we have also used CK++ data set for estimating the performance, okay, or measuring the performance. Because if you do not have the benchmark data set, you cannot have good publications. So it is always suggested that you should have a benchmark data set over which you will apply your algorithm and then measure the performance. Okay, so we have used JAFE and CK+ data set. As far as these points I have left out, I will explain when the corresponding slide is popping up in detail so that you can understand it correctly. These are all some of the sample emotions from CK+ data set. Okay, CK stands for Cohen and Kanade. Okay, this is also very popular data set and many people do use it for the research purpose. Say you have neutral, meaning that the expression of the person is neutral, neither joy, surprise, anger, fear, disgust, sadness. Okay, so he is or she is, the object or subject is neutral, the facial expression is neutral. And the second one, you can say this is a joy expression, right? So you'll see that the lip is deformed and the nose is deformed, eye is deformed, eyebrow is deformed. Okay, chin and cheeks all are getting deformed from this, right? So this is joy expression. And you also have surprise. You can see this fellow got enlarged, and it's a kind of exclamation. So every part of the face is, or every component of the face is deformed. So this is surprise. Similarly, the anger, the fear, disgust, and sadness. So in general, there are a set of expressions or known expression, which is, say, 1 joy, 2 surprise, 3 anger, 4 fear, 5 disgust, 6 sadness. So in general, people do call there are 6 basic expressions formulated. People do always that there are 6 basic expressions such as joy, surprise, anger, fear, disgust, and sadness. In addition to that, you will have one which is neutral. The neutral is not kind of any expression, but this is very useful subject or useful status, that is neutral, because any comparison you do compare with the neutral face and saying that okay, the expression is surprise, expression is anger, expression is fear, disgust, and sadness, etc., etc. Okay, this is how things are happening, right? Any clarification from anyone on this? Anybody would like to know? Any clarification? Am I audible? Am I audible?
Yes, sir.
Yeah, I'm audible. Okay. No clarifications, right? No clarifications. Okay. Now, similar to the CK+ data set, and we have the Japanese data set. It's called Japanese female. These two stands for Japanese female facial expression data set, right? So similar to that, you have neutral, you have joy, you have surprise, you have anger, fear, disgust, and then sadness. Okay, so here also you will find that 1, 2, 3, 4, 5, and 6 basic expressions or emotions, right? So, these two slides we have deliberately, or I have deliberately brought in such that the participants will know that there are 6 basic emotions and the neutral is the one which is being used as a reference. And there are 2 data sets. One is CK++ data set and another one is Jaffe data set. In addition to these 2 data sets, we have a number of data sets, but these 2 are very popular, right? Now, another example, okay, is, say, there is a concept called action units. What do you mean by that? If you consider any phase, say for example here, so this is the phase. Now, computationally, how do you model this? Because we are from computer science, right? You need to model computationally. The psychology people will model it in a different way. But being the computer scientist, we should model the entire phase, and the concept which is being used is called action units. What do you mean by action units? Say here, I say action unit 1. What do you mean by that? If there is, the inner eyebrow, okay, inner brow, say for example, this and this is getting raised. When it will get raised? For an emotion, for an expression, okay? So this AU1 refers to the inner brow raiser. Similarly, the action unit 2 is outer brow, okay, the outer brow, right? So, is there a change, is there a deformation, right? Then I denote that as action unit 2. Similarly, for action unit 5, I connect the upper eyelid, okay? The upper eyelid is being connected with action unit 5. The nose wrinkling, okay, the nose wrinkling is action unit 9, and the cheek puffer, this one, okay, this is action unit 13, and lip tightener, okay, lip tightener is action unit 23, the lips part is action unit 25, and squint is action unit 44. In general, there are 45 action units. I have given some of them for better clarity, otherwise the slides will be untidy. So there are 45 action units, and each and every action unit is pertaining to a particular component of the face. Component in the sense, eyebrow is a component, nose is a component, lip is a component, upper lid is a component, right? So likewise, each and every component of the face is denoted or modeled with respect to an action unit, and whatever is happening with the action unit is being processed, and from which the expression or emotion of a person is being estimated. Please do remember, I say a term estimated, not calculated. It may not be so accurate as possible, and that is the purpose we have classifier, and it will learn from the partial data to give the paka answer, right? So this is what the important thing before we get into the research perspective. Now, in this paper, the paper which I am going to discuss, it has a lot of objective, and this fellow, takes care of the effect of illumination, the method we have proposed. And the feature we are extracting is scale, orientation, and translation invariant feature. Okay, I'll explain this. And it will also take care of handcrafted images, and then it will extract the feature from that. And it improves the programming and computational cost. These are all the important things from the paper we published, and then I'm going to discuss. So as all the research papers, we also have various stages. The first one is the pre-processing stage. The second one is the feature vector extraction stage and the classification stage, right? So these are all the three stages. Then I will explain each and every stage for you, right? So as far as the pre-processing is concerned, this is the block diagram of the entire work. So you get the input facial image. You have seen, the facial image is being given as input, right? So you got this, you got this, you got this. Okay, so you got the facial image, right? Then any facial image you got, say you might be having an image like this. Okay, and here is the face. Now all these areas, the rest of the areas, I'm not really interested because I'm looking for the face. So you need to have a separate algorithm, and that algorithm will localize the face. Localize in the sense that it will locate where the face is available in the entire image, right? Then this process is called the face localization. And once you got the localization, you have to bound it. Say, for example, this is the boundary by which you process and segment the face into square regions. Okay, so then you take these out. Then eye is the segment, nose is the segment, lip is the segment, forehead is the segment, chin is the segment, cheek is the segment. Likewise, you need to segment it. So all these business happens in the pre-processing. So from here, once you got all, now we will be extracting the interval graph. I'll tell you the process, very, very interesting. Then you will calculate the degree of deformation. This is called the feature vector, right? And then do the classification, right? Quickly we'll go there. So the pre-processing I will skip and then directly get into the feature vector. It will be very interesting. So this is basically an image from a data set, very popular data set. Now we can see that the entire face is being represented in a different way. So you got a circle, you got a circle, you got a circle. In the or at the first site, okay, at the first site, you may not understand what is this all about. A lot of balls and rounds and etc. etc. But being a researcher, okay, it is nothing but a graph and consisting of vertices and the edges. So it is basically graph, and these are all the nodes, okay, and these are all edges. Okay, this is the edge, this is the edge of the nodes, edge of the graph, edge of the graph, edge of the graph, right? So in the first site, you may not really understand this is something, but as a computational expert or computer science faculty member, you should understand this as a graph. So whenever I say this is a graph, the graph consists of set of nodes or vertices and set of edges. So it can be represented in the form of G is equal to V comma E. V is number of vertices and E is number of edges connecting all these vertices. This is how a graph can be formulated. Now once this is being structured, please do recall that I was talking about a concept of action units. Means what? Each and every component of the face can be monitored using action units. Because if something happens in, say, nose, you will say that, okay, there is an emotion related to that. Now, there are 45 action units. I felt that these 45 action units are not at all sufficient to measure the expression very correctly or effectively. So I have introduced the action units, okay, and place the vertices wherever it is possible. So anything happens at this junction, then I can measure it. Anything happens here, I can measure it. Anything happens here, I can measure it, right? So I have made this as a dense graph right? So that is the first and foremost work of the research I am discussing. So once you have made this graph, then what I am going to do, the entire graph I am segregating into 4 regions. This is for operational convenience. Okay, I hope you can visualize this. So the first region is denoted as R1, second region is denoted as R2, third is R3, and final one is R4. As I said, it is for operational convenience because the face, the face can be modeled, or face can be mapped as 4 regions. That's what we found. And considering the nose as a reference point, you will see that nose is in the middle, somewhat middle of a face, anyone's face, and if you keep that as a reference point, and then you can have 4 regions, right? And each region will be a small region so that you can manipulate very easily, right? So, as I said, I have region 1, region 2, region 3, and region 4. And these regions are, divided physically, okay? So that the contribution of salient points in each of these regions is measured. Now, earlier I said action units. Now I am introducing a concept called salient points. Okay, salient points. What do you mean by that? Say salient points I am saying, which is SP and belongs to V. What is that? I told you earlier that I have a graph with vertices and edges. Now I have region 1. Okay, so region 1 will have, say for example, sum of vertices V dash. Okay, so V dash is nothing but sum of the vertices in, say, R1, and this V dash I am denoting it as salient points. Why I am calling it as a salient points? Now, in the face, I have identified some of the points. For any emotion, you will find some kind of deformation in those points. So, if there is a change in those points, it is useful for me to classify the emotion or determine the emotion. And that is the reason I call those points as a salient points instead of action units. So, as I said, for each and every region, I will have the salient points. So, R1 will have a set of salient points, that is here. R2 will have set of salient points. R3 will have set of salient points. R4 will have set of salient points, right? So this is how the initial modeling. Now you can see further, decomposition or further understanding. Now I am introducing a concept, okay? Say this one, the region. Now for this region, I will have a graph G of I, meaning that the G of I, if I say G of 1, then the graph is related to the region 1. If I stands for 2, the graph is related to region 2. Similarly, so I will have set of vertices. These vertices are denoted as salient points. Now, what I am trying to do is, the salient points are connected through edges. Okay, salient points are connected through edges. Now you will see that, say you have vertices like this, and this is connected to this. Say if we call this as 1, 2, 3, 4, these are all the vertices, and this fellow is connected like this, then it is a graph for me, and all of us know. And here we have shown only this connection, but internally during the computation we have taken this connection also, because deliberately we have avoided in drawing that, because if I have drawn it, it will be untidy. So we have avoided it, but internally it will be like this. So you will have a node, you will have a node. Okay. So meaning that all the nodes are connected to each other, right? And these nodes is, it's a salient point. If there is a change, then we will measure it, right? Okay. So given this, kind of introduction to our method, now I will explain a concept of the interval graph we have, extracted from the common intersection points. Before I explain this, I will take an example. Say, I have a graph like this. Okay, so I have 4 vertices and 4 edges. Now, the concept of interval graph is such. Now, at a given point of time, in the sense during a particular interval, that is why it is called interval graph. During, for a particular interval, in the sense that there is a time window, say for example t. Okay, so you got t1 and then t2. During this period, you laugh, say for example, someone laughs. If someone laughs, it is an expression. So it's not that all the nodes will be, all the salient points will be deformed. Okay, meaning that when you laugh, your nose is doing something, your eyes are doing something, your mouth is doing something. So, say for example, this is the mouth, then when you open your mouth, this node 1 goes here. Okay, and node 4 goes here. And node 3 goes here. And node 2 remains in the same place. So, what do you mean by that? During the interval t, the node 1 has moved, node 3 has moved, node 4 has moved, that is the salient points. So now I am connecting it again. See, now I am connecting, and this is the graph. You see the graph. Now it is got deformed. This is the initial graph. This is the deformed graph. Means this fellow has deformed, and this fellow has deformed, this fellow has deformed, and this fellow remains in his place. So now I extract a graph from the initial graph, that is 1, 2, 3, 4, that I will have the information on the edges which is connecting, okay, which is connecting 1, 4, 3, okay. Say for example, 1 is moved from here to here, 4 is moved from here to here, 3 is moved from here to here. So I will have all these information, the edge. Okay. Now with this information, I will find out that which portion of the face got deformed from the interval graph for a particular time t. Then I will say that the emotion will be, say, happy, disgust, angry, cry, etc., etc. So whatever I explained here is the one given in the form of an equation. So I thought I'll explain the concept first and then go to the equation. The equation is also not kind of, a satellite kind of equation. It's a very simple graph representation. Okay. Now let us get into this. Say for example, the interval graph will have the common intersection points. Means, so this fellow is moving, this fellow is moving, this fellow is moving. So these 3 nodes or these 3 vertices commonly had intersection. So I will have only the information of them in a graph that is called interval graph, because it has happened in a particular interval, right? And what I am going to do, say for example, I consider only region 1, and region 1 I said can be represented in the form of a graph, and again it will have vertices, edges, and also phi 1. This phi 1 symbol is for the interval graph. Please do remember, now I have 3 information. The first information on the vertices in region 1, The second information is on the edges of region 1 and an interval graph of region 1. The interval graph is nothing but similar to the one which I have explained. So from the interval graph, I'll understand. So what will happen? You know, V1 will have vertices, E1 will have edges. Now what Y1 will have? Y1 will have set of edges of size K. The size K will be, okay, K will be less than or is equal to V. Okay, or edges. Less than or is equal to edges. Because the interval graph will have the information of the edges. Okay, so here say for example E12, E13, E14, 17, 18, 19, 20. These are all the edge information. So this fellow will have edge information, right? The edge which has deformed for a particular interval is called the interval graph. Say as I said, V11 have moved to V11 dash, V12 have come to V2, V12 dash. Likewise, okay, the graph changes, and that's what I have explained. Okay, now I give a pass. If you have any questions, queries on this concept, I can make you understand. Maybe 1 or 2 seconds we can make a break. Anybody have any queries, questions? Please do interact. Don't make this session monotonous. Anybody? Any faculty? No one? Jennifer left the meeting. Anybody have any question? Gokulapriya madam, do you have a question? Saravana Kumar, do you have a question? Valimail madam is there. Valimail madam? Hello. Oh, you are not, you cannot talk or what? The host has muted you, it seems to be. Right? Okay. Now, okay, again I'll go make my this thing. So with this understanding, let us proceed further. So similar to the region 1, I can also have the interval graph for region 2. Then I denote that as G2. Then you will have vertices, you will have edges, and you will have interval graph. Now the vertices will be like this, interval graph will be like this, sorry, edges will be like this, and you will have interval graph with the set of edges moved and of size K1. As I said, K1 is less than or is equal to E2. E2 is your edges, right? And now if I generalize this, I have a GI. GI is a graph where it will have vertices, edges, and the set of edges which has moved are having the common intersection, and that could be denoted as like this. Okay. So now we have, say for example, found out which one is moving, and now say I have something like this. Now the 2 has moved from here to here. Now I call this as 2 dash. Previously the edge is like this. Say it is E1. Now since this fellow has moved, I connect this with say E1 dash is the edge, and this become 2 dash. Now you see that this is 1. Another one is, say from 2 has moved like this. So it has become 2 dash. Now what will happen? This is E1 dash, this is 2 dash, but this fellow has moved in this direction, okay? And this fellow has moved in this direction. And here he has moved, say for example, some little length, and here he has moved, say for example, if it is 2 dash, he has moved far away. So there are two concepts we have proposed. One is degree of movement. Okay, so how far this fellow is moving, and another one is the direction, whether he is moving in positive direction, I mean left hand, right hand, likewise. So the degree of direction is also calculated. So what we have done, the deformed direction is the one, I mean this formula is proposed by us. Okay, so this is called degree of direction and degree of deformation. Degree of direction says whether you are here, okay, or whether you are here. This is talking about the direction. Deformation is how far you have gone or how close you are. Okay, so these two we proposed our own kind of understanding and then calculated it. Okay, so the degree of direction is this, where you will have set of vertices and denoted as pi. Pi is nothing but the interval graph, right? Now it can be calculated, it can be denoted as saying that you have two vertices u and v in pi of I, because the u and v has to be part of the interval graph, okay, and it is connected through an edge E. Now both the u and v, both the vertices may have deformation in either in vertical direction or in horizontal direction or in diagonal direction, right? Now it is up to us, or it is, you have to measure in which direction this fellow has deformed, right? So given this scenario, and this is the formula, is called the degree of direction of u. Okay, so since you have two nodes, u, and then degree of direction of v, okay, whether it happens in vertical, horizontal, diagonal, as far as u is concerned. Similarly, as far as v is concerned, whether it is vertical, horizontal and diagonal. Because you know that the image is nothing but a two-dimensional matrix for me. And if it is a two-dimensional matrix, right, you will move along the horizontal, you will move along the vertical, and you will move along the diagonal direction, and that needs to be captured. Okay, so using this formula, and this is how we measure u of I, okay, any node in diagonal direction, and this fellow is also in diagonal direction, and they are belongs to pi, and that is being measured like this. I mean, if you have something similarly in the this thing interval graph, you have set of components where all the components are moving in horizontal direction and all of them are belongs to the vertices, and I am also having another interval graph where I will have all the nodes moving in vertical direction. Please do remember, all these three interval graph is subset of the first interval graph, and this fellow will have all the information of the diagonal movement, and this fellow will have all the information of the horizontal movement, and this fellow will have all the information in the vertical direction. So diagonal, horizontal and vertical. Now the entire interval graph, whatever we have discussed, is decomposed into further three for understanding, right? Now this is the formula. It is called degree of deformation in diagonal direction, degree of deformation in horizontal direction, degree of deformation in vertical direction, and this is nothing but we are calculating the distance of a node u, okay, in diagonal with the node which is deformed. Say for example, if I have 1 here, now this 1 is connected to 2, say for example. Now the 1 has deformed here. Now this fellow has become 1, Now this distance, it has come in horizontal direction, vertical direction, and this is pixel 1, pixel 2, pixel 3, and the distance will be in the numerical value. Say if it is in 2, if it has come to 5, then it is 2 minus 5, okay, which is becoming minus 3 in modulus, so it will be 3 as a distance. Similarly, in the horizontal direction, you can measure the distance and it will be a numerical value, and here also it will be a numerical value, here also it will be a numerical value. Finally, whatever values you got from the diagonal, from the horizontal, from the vertical will be summed up, and then it is available in this value. So now what will happen? I am constructing a feature vector. I call this as FP, where you will have all, okay, the degree of direction of U, degree of deformation of V, degree of deformation of UV, and this kind of thing, the total, right? So put together, I consider this as the feature vector. So for measuring or estimating the emotion from the human face, this feature vector will be used. From there, we can estimate whether a human is in angry mood, disgust, happy, cry, laugh, etc., etc. Okay, so this is what the core concept by the interval graph, by using the interval graph, the feature vector, whatever we have used. If anybody have any question, please do interact. I'm feeling awkward that no one is here. I am making a lot of blah blah. Anybody is there around? You are all there. There are 26 logins. Okay, I am not even listening a single kind of thing. Prabhakaran, hello, are you there? You logged in and then went away. Damodaran, Vignesh, Jennifer, Kannadasan, oh, you are all there. Any question, Damodaran? Thanks for at least interacting with this text. If you have anything, please, you people can send me the query in text. Any question from anyone? No question, right? Okay. So if no question, again I'll proceed with the next topic. Next topic in this next research of the facial expression. But here we have used a different concept. Okay. So now the concept we have used is only the lip. Earlier, we have used the face. Now we thought, let us get closer to the face and then move with all the components of the face. Say, for example, if you have a face, okay, if you have a face, now you have eye, forehead, nose, this one I'll draw nicely, mouth, okay, this one, okay. Now, this is the component and this is the component, this is the component. We thought, let us get into closer to the components. Say, the lip we have used. Is there any contribution from the lips in recognizing the facial expression? That was the problem. And we have solved it. The paper is published in Cognitive Neurodynamics. Okay. And it is available in this DOI. It's a Springer journal with high impact factor. Right. Now let me progress. So objective is same. Now the stages of research, right? The novelty, etc., is there. I will not stretch more, right? I will not stretch more. Straight away get into the problem. So this is the block diagram, right? Now, as we have discussed earlier, you get the input facial image. Now the algorithm will work for localizing the lip. As I said, if you have the facial image, right, you have components, but this time I am interested only in lip, so my algorithm will work to localize the lip, then bound it with a boundary and segment it so that you represent like this for understanding the movement over the lip, right? And after that, the second stage, this is the first stage, this fellow is the second stage. You extract the feature, right? Then you do the classification. This is the third stage, do the classification. And here you kind of pre-processing for the classification, which is the segmentation, etc., etc. Right? Now, given this understanding, now let me get into the problem. Before getting into the problem, there is a small understanding you should have. So I'm skipping a little bit and then go directly to this. Say, you have a lip here. Now, say if I have a lip, say this blue color, and this is looking like this, right? So what we thought, if you work on any research problem and you want a good publication, there should be a strong theory. Okay, there should be a strong theory. Now this theory says that this fellow physically looks like a parabola. Okay, the lid looks like a parabola. Now, if you want to rely on this, can we use the mathematics of parabola? That's what the understanding, right? Now, given this introduction, let us go back and then discuss some sort of small mathematics. Okay, so that is the purpose we discuss the properties of parabola here. Okay, so now the parabola is nothing but a connection of multiple points. Say if I have a parabola like this, it is nothing but a point here, a point, a point, a point, a point, a point here. Okay, so this is how a parabola can be considered as a multiple points, right? So multiple points so that you can get the fixed lines. And these fixed lines are called focus, okay? And there will be a kind of a term called directrix. Now, say this is the parabola, right? And this we are trying to model a lip. Now, if you have a parabola anytime, the parabola will always have a directrix which will be running a perpendicular, okay, the line, and again on the 90 degrees. So sorry, this is the perpendicular one, and this fellow will hit or intersect the parabola, right? So say for example, this point I am calling as P1, P2, P3. Why I am considering this as a point? As I said earlier, a parabola is nothing but interconnection of points. So this is a point, this is a point, and this is a point. Now, this is perpendicular, this is perpendicular, this is perpendicular to the directrix. Okay, and this fellow is another line, and which is called as vertex. Okay, and another important point in parabola is the focal point, right? So we should use the concept of directrix, you should use the concept of vertex, and you should use the concept of focal point to model a parabola. And if you model a parabola, then you can successfully understand the characteristics of the parabola. Once you successfully understand the characteristics of parabola, then you will understand the characteristics of a lip. And wherever it moves, basically the parabola moves. Okay, so when there is a movement of parabola, the focal point, etc., getting disturbed, from this disturbance, you can understand what is the emotion, expression, etc., etc. Okay, So given this mathematical understanding to you, okay, I don't want to again explain what is a parabola. Say for example, this point, P1, and F is the focal point. It can be calculated using x1 comma a and y1 square. This is the pure mathematics we have studied in our +1 +2. Okay, to understand the characteristics of the parabola, I don't want to again repeat and then make you bore, right? Okay. So now what is happening here is that when you model a lip as a parabola, there are two conditions you'll have to see. Say for example, the equation 9, y square is equal to 4ax. It's a kind of linear equation, right? And any point in the parabola, say if I have a point here, a point here, a point here, a point here, also there is a point here. Please remember there is a point. Now if I say point number 1, 2, 3, 4, 5, I will say all these points up to 4 are falling over the parabola, but the point which is, point number 5 is not in the parabola. Why? Because it violates the characteristics of the parabola equation which is given in here, which means that any point which is falling over the parabola should satisfy this equation. If it doesn't satisfy, then you can declare this fellow is not part of the parabola. So this is the point you should understand, right? So as far as this is concerned, all the research and other things we have done to confirm that, okay, equation 9, 12, equation 9, 12 conforms the focus, etc., etc. A little bit deeper mathematics. If someone is really interested, you can discuss whenever you have time, etc., etc. Then we will take it up, right? So these are all the observation of parabola based on this. Okay. Now I have got all. Now one more the concept. Say here, this is called multiple intersection points on the parabola, because as many number of points you want to have over the parabola, you will have control over your lip region. Okay, so I would like to have multiple regions. So once you have multiple regions, you can manipulate this, you can understand this, you can understand this, you can understand this, you can understand this, so that the computational efficiency will increase. Okay, so now without delaying it, let us have this. And this was the first picture I have explained you. Now again, see, this is the lip. You now, since you have seen all this, say, this is my parabola, and this is my y-axis, and this is my x-axis, right? I will use nose as a reference. Now with y-axis, I have my directrix, okay, the rectum. All those points I have, say, I call this as a B, I call this as A, point D, point M, M is at the middle, C, O. So whatever points I have, say, in my parabola, I have modeled the same thing, say point number C, point number A, point B. So the same thing I have modeled over the lip. Now I also have the focal point, because any parabola in the world will have its own focal point, which is denoted as f of A0, right? Now with this understanding, now let us go further, right? Okay. Another important aspect of this feature is scale invariant. Why? Say this is a scale. If I am mapping this lip as a parabola, I will have the same structure. I will have the same structure. Now I am scaling down, you see the same structure. Again, further scale down, same structure. Further scale down, same structure. So this is same image represented in different scales, okay, and but still I am in the position to represent my parabolic equation or parabolic representation over the lips. So that is why this feature is called scale invariant. rotation invariant. This is very beauty of the proposed method. You see that it's a original 45, 90, okay, 180, 270, right? So this is rotated in many direction, but still you find that, okay, I can map the parabola because I consider nose as the region and then do it, right? So this is the rotation invariant property. Now we will get into the method one by one. Say our pre-processing algorithm will work and then localize the leaves like this. It was a smaller region. I have enlarged in a bigger way, scaled it up so that we can view it. Once I do that, I superimpose a two-dimensional matrix kind of grill. Okay. And this grill, anyway, because you know that image is nothing but a two-dimensional matrix. And to understand the concept of the two-dimensional matrix over the on the lip, we have drawn it, right? So now it is superimposed over the lip. Now you can see this one, the yellow color portion, I am considering as an upper lip, okay, and the green one I consider as a lower lip. Now, once I consider like this, again, I have to do a perfect job saying that because this two-dimensional matrix stretches in many places, okay, many places. Now, I love to identify a point, say for example, the points under green, points of green is falling inside the lip. I'll use the parabola equation, a point which is contributing to the parabola. Now we'll see that these blue points, okay, these blue points are points but which is not contributing to the parabola but outside. So I will have some kind of equation, right? So this is upper, okay, this is lower lip area, region 1, region 2, and by this I will identify, okay, whether a point is falling inside the region or outside the region, okay, and this is how it is, right? So having said this, this is how we come to know about the points which is contributing to the parabola. Now you can see that I am drawing a line again as a parabola. Now all the points which is satisfying the equation which we have discussed earlier will be taken into the consideration. Now that I am modeling as a predicate calculus, okay, meaning that if a point is contributing to the parabola, is modeled in the form of a predicate logic saying that whether it is yes or not. So this is what it is. Again, if I am explaining, you will be getting confused. Okay, so there is a point x comma y, and there is a focal point, and these three will be combinedly seen to know whether a point is contributing to the parabola or not. Okay, so that is how these two equations are used for the both upper and lower lips. Once it is done, then that's it. That is the feature vector. Then you will do the classification. Now, whatever we have used, that is the interval graph. Okay, that is a separate paper. Now it is the parabolic property. Okay, parabolic property of the lip. This is a separate paper, but both of them have used, most of the machine learning algorithm for the classification problem. By this time, you will definitely understand that machine learning algorithm is not at all a research. It is a tool anyone can use for, measuring their performance. But the research lies here, okay, proposing an interval graph with novelty, proposing a kind of parabolic properties of the nose has a novelty compared to the other kind of thing. Now, for both of the cases, we have used, the support vector machine, MLP, multi-layer perceptron, that is the neural network, and random forest algorithm. Now, let us see what is that. Say, this is how TS, this is the training set. The support measure vector machine takes a kind of the training set and then get it trained. So you have the point, and it gives you its class is CJ. The CJ is nothing but the various emotions, and can be represented in the form of relation with a certain dimension, right? Now, the sample output of the SVM is like this because it is a multi-class, because you will have angry, you will have sad, you have disgust, you will have cry, and you will have neutral as well. So it is a multi-class problem, and that is how the output space of a typical SVM will look like. And similarly, as far as MLP is concerned, so you will have a point along with weight, you will have a point along with the weight, you will have a point along with the weight. Once you train it, then it is your duty to update the weight value so that you get required output. That is the whole concept of multi-layer perceptron. And then the final one, we have used the random forest. Random forest is nothing but, this is a kind of decision tree 1. This is a decision tree 2. This is a decision tree 3, and this is a decision tree 4. Now, this fellow gives, say, for example, angry, and this gives angry, and this gives disgust, and this gives angry. So now the voting will be there, whichever is maximum. So angry is maximum. So the classification of the data which has gone in is angry, and this fellow last. Okay, so majority voting is being done. That is the purpose of random forest. It comprises of the decision trees. Okay, so with all this, we have done this, right? So here also you will see that various points, etc., right? And again, it is very known to you. Okay, so this is what we have done. Now, I am giving you around 10 to 15 minutes for question and answer. Please make it interactive, otherwise, kind of thing. Yeah, let me open this, stop sharing. And this is what we have done. If any one of you have questions, queries on anything, please let me know. We can take 10 to 15 minutes because 10 to 15 minutes is a good time for interaction. Any questions from anyone? Madam?